Hi there, welcome to another episode on the Arduino series. Last time we introduced a simple program to run on the Arduino to measure frequencies, and we found that although the measurements were correct, the Arduino was not able to reliably measure frequencies above 1.2 kHz. Today we will put together another frequency counter based on the Arduino. This time, however, we will be able to measure frequencies in the range of a few megahertz, which is a huge improvement over the last time. Let's see how this can be done. Once again, we won't need several components to make this frequency counter. Actually, we will use the same components as last time, although we will have some limitations on the Arduino pins due to specifications of the new library we will be using. Like last time, we will use the Arduino prototyping system that I built some time ago. This sort of mini-lab will provide us with the Arduino Uno itself, a 1602A LCD, and a breadboard to make all the connections. We will only have to add a potentiometer and a resistor to be able to use the backlight of the LCD and to adjust the contrast of the display. Here is the new program that we will run on the Arduino. We are still using the liquid crystal library, like we did the last time, to be able to easily control the LCD. We will also use a new library called Frequency Counter, which is specifically designed to measure frequencies with the Arduino. Before being able to compile this code, we need to make sure that both libraries are installed in the Arduino IDE. We still have a variable where we will store the measured frequency. However, this time the variable is an unsigned long instead of the floating point variable we previously used. The line to instantiate the LCD object is slightly different. In fact, the frequency count library wants to use pin 5 as the input of the frequency counter, and also imposes some limitations in the use of pins 3, 9, 10 and 13. To avoid any possible interference, I therefore avoided using pins 3 and 5 for the display, and instead I used the available pin 1 for the enable signal and pin 12 for the D5 signal. Let's go now to the setup and loop functions. The only thing we need to do in the setup function is the initialization of the frequency count library. The begin method of the library needs only one parameter, currently set to 1000. This parameter defines the resolution of the frequency counter itself. Since it is set to 1000, the library will make measurements in Hz. However, if we set the number to 100, the measurements will be in tenths of Hz, and if we set the number to 10, we will be measuring in hundreds of Hz. And if we set the number to 1, we will be measuring in thousands of Hz, or in other words, in kilohertz. The frequency counter library provides two main methods. The first is the one called available. We will need to test the return value of this method before attempting to read the frequency. Only if the return value is true, the read frequency will have a meaningful value. And so, we actually test the return value of this function in here, and then we execute the read of the frequency value only if the return value is true. At that point, we also clear the display, we set the cursor to the beginning of its first line, and we finally print the value of the frequency and the measurements unit. I also put a delay at the end of the loop function, so it will wait a short amount of time before running again, and that will avoid the flickering of the display. Here is the schematic for this frequency counter. Those of you who watched the previous episode will recognize the similarities with that schematic, and in fact the schematic is practically the same, with the exception of the usage of two pins that I had to repurpose because of the needs of the frequency count library. Let's take a closer look. We have an Arduino Uno on the left and a 1602A LCD on the right. A 10K resistor is connected to pin 3 of the display to provide a contrast control. Moving the potentiometer cursor from one end to the other allows us to apply a voltage between 0 volts and plus 5 volts to pin 3, which modifies the contrast of the display. The display is also illuminated through a backlight provided by an embedded LED that we can power through pins 15 and 16, which are respectively the anode and the cathode of the embedded LED. Resistor R2 of 220 ohms limits the current into such LED. The power supply for the display comes from the Arduino itself through its 5 volts pin, which is connected to pin 2 of the display. Pin 1 of the display is connected to ground, as well as the read-write pin, which is not used in this application. The information on the display is provided by the Arduino via a 4-bit data bus. This is made by pins 11, 12, 13 and 14 on the display side, and by the data lines D4, D12, D6 and D7 on the Arduino side. The information is multiplexed on this data bus with the help of the signals RS and E on the display, which are controlled respectively from pins D2 and D1 of the Arduino. The frequency under measurement is injected on pin D5 of the Arduino, and it must be a TTL signal. In this case, we assume to always use TTL signals. However, if we need to use different kind of signals, we can still put in front of pin D5 a Schmitt trigger to transform an irregular signal in a precise TTL signal. Although I did not show this on the schematic, the Arduino needs to, of course, to be powered either through its USB port or through the power supply connector on the board. Let's now take a look at the assembled prototype and let's see how it works. Here is our new version of the frequency counter, built around my Arduino prototyping system. Visible here are the Arduino Uno board on the left, a clone actually, the 1602A LCD on the right, and the potentiometer to tune the contrast. I already made all the connections using these jumpers. Such connections are basically the same as in the previous version of the frequency counter, only changes are on those pins we discussed earlier when we examined the schematic. Let's now connect the device to the computer, upload the new code and test it. Here is the USB cable coming from the computer. Here is the Arduino IDE with the code ready to be downloaded. Let's now compile the code and upload it to the Arduino board. Okay, all done. Back to the circuit now. And you can see that it is already showing a 0 Hz on the display. This is the potentiometer to tune the contrast on the display. Okay, let's leave it this way, it seems perfectly visible. Let's now connect the frequency counter to the wires coming from my function generator output. The function generator is currently providing a square wave at a frequency of 1 kHz and an amplitude compatible with TTL circuitry, which is a square wave going from 0 to plus 5 volts. So let's take a look at the frequency measured by the Arduino. And we can see that the display is already showing a frequency of 1000 Hz. Let's now decrease the frequency provided by the function generator so we can determine the lower boundary of the frequencies that this circuit can measure. I'm down to 500 Hz, and the Arduino is measuring it right. Now down to 100 Hz, and it is still fine. Now 50 Hz, okay. 30 Hz, still very good. 10 Hz, and still fine. Now it is 5 Hz, good. And now 1 Hz. And the measurement is still perfect. So it looks like this frequency counter is perfectly capable to go down to 1 Hz, which is the minimum measurable frequency since the measurement is contained in an integer number. Let's now see what the upper boundary is. So let's go back to 1 kHz. And now, if you remember the circuit from the previous video, that was able to measure fine up to 1200 Hz. Let's see if we can go any further than that. So let's start trying with 5 kHz. And yes, this version of the frequency counter still measures it quite well. So let's go now to 10 kHz. And look at that, we are still fine, and the measurement is accurate to better than 1%, which is great given the simplicity of this circuit. I am at 50 kHz now, and the reading has still a precision better than 1%, and it is very stable, no considerable flickering. Let's go now to 100 kHz, and again we have a good reading with a precision better than 1%. Let's now jump to 1 MHz. And look at that, still correct reading and the same precision. Now 2 MHz, 5 MHz, and we still have a good reading. 6 MHz now. And now 7 MHz, and it is still working fine. Let's go to 8 MHz. Now the precision is degraded, which tells us that we have reached the limit of such frequency meter. At this point, I will say that this circuit works very well at frequencies from 1 Hz to up about to 7 MHz, providing a very good resolution with an error of less than 1%. Well, it seems to me a pretty good result. So now we have a very cheap frequency counter built around an Arduino Uno board, very effective and precise, that we could use as a regular lab instrument. If you are in the market for a frequency counter, but you don't want to spend a lot of money and you don't need to do measurements above the 7 MHz limit, think about what you have seen today. Spending just a few bucks for an Arduino Uno, an LCD and a couple more components, you could actually build your own frequency counter using the schematic and the sketch I showed you today, and available at the link provided in the description below. Very easy to do and with very good overall precision. And if you happen to have a teensy board, know that the library we used today is compatible with that board as well, and will allow you to go up to about 60 MHz rather than 7, according to the library documentation. I didn't try it. Not bad for a cheap lab instrument. In the future, I will try to exploit this Arduino-based frequency counter for the upgrade of a device that I built a long time ago and that I have enjoyed using to play music. Can you guess what that device is? Try answering in the comments below. And in the meantime, I'll see you in the next video and happy experiments!